Hi everyone, this is Mrs. GA, and today we're going to talk about exponential and logarithmic functions. Alright, let's start by looking at exponential functions. So the exponential function with base a is defined by f of x equals a to the power of x. So we call this the base, and this, of course, is our exponent. So there's three types of exponential functions you're going to see. First one is if a is greater than 1, we're going to have what's called exponential growth. So your graph is going to look something like this. It will always go through the point 0, 1, because anything to the power of 0 is equal to 1. And exponential functions, the parent function has a horizontal asymptote at y equals 0. So it's going to get really, really, really close to the x-axis as x approaches negative infinity, but it will never quite reach it, because if you think about it, it's impossible to take any base, raise it to a power, and get 0. It's also impossible to take any base, raise it to a power, and get a negative answer, right? Even negative exponents, as we know, they don't make your answer negative. They cause a reciprocal. So the second type of exponential function you might see is exponential decay. So that happens when your a value, your base, is between 0 and 1. So this graph is still going to go through the point 0, 1. However, it's going to be like this. So it's going to decrease as x approaches positive infinity. Now for this one, we still have a horizontal asymptote at y equals 0. Right, because any base to any exponent can never equal 0, and it will never become negative. However, again, for a base that is between 0 and 1, you will experience exponential decay. So as your exponent gets larger and larger, your y value gets smaller and smaller. The last type of exponential function you might see is an exponential function with a base of e. So remember, e stands for an irrational number. So e is approximately 2.718. So if you ever have a base of e, we experience what's called continuous growth. So we still go through that 0.01, and we still have a graph that is going to increase as x approaches positive infinity, and we still have that horizontal asymptote. However, you'll see when we start to do some application-based problems, if we want to have continuous growth, we will use base e. It looks just about the same as an exponential growth function. It's just a very specific case. All right, so now we know what the general types of exponential functions are. Let's see if we can graph them using transformations. So for this one, we're going to use p of x equals 2 to the power of x as our parent function. So we're going to be graphing base e, or base 2 exponential functions. So for this, maybe we can start by actually making a little t-chart of some of our values from our parent function. So maybe let's do -1, which would give us 1/2, 0, which would give us 1, 1, which would, of course, give us 2, and 2, which could give us 4. So let's sketch a really quick graph of this so we can see what our parent function looks like. Okay, so here you can see that we have exponential growth, and we have our horizontal asymptote at y equals 0. So let's see if we can look at f of x. So here I see that we have two transformations. We have a vertical shift up 1, and then we are going to have a horizontal reflection over the y-axis. So remember, we can get some coordinates for this by actually transforming our coordinates. So we're going to be multiplying all of our x values by -1, and then we would add 1 to all of our y values. So this will be our horizontal reflection, and this will do our shift. And I do want to point out that since we're shifting vertically, that will shift our horizontal asymptote up 1 as well. So let's see what we get here. For our x values, we get +1, 0, -1, -2. And then for our y values, we get 3/2, 2, 3, 5. So let's sketch a graph of this below. Okay, so if you look here, now it looks like it's an exponential decay function, and of course that was due to the horizontal reflection, and you can also see that everything was shifted up 1, including our horizontal asymptote, which is now at y equals 1. All right, and let's look at part B and see if we can graph g of x. So here I see that we have 2 transformations. We have a vertical reflection over the x-axis, and here we're going to shift to the left 2. So to change our coordinates, we're going to do x minus 2. That's going to shift all of our x values to the left, and then we're going to do negative y for our vertical reflection. So again, I'm going based off of my parent function coordinates here. So this gives me negative 3, negative 2, negative 1, 0, and then negative 1/2, negative 1, negative 2, negative 4. And let's sketch a graph of that below. Okay, so here's a sketch of the graph. So you can see that from our parent function, it was reflected vertically, and then it was shifted to the left 2. Please also note that since we didn't have any type of vertical shift, our horizontal asymptote remains at y equals 0. All right, so go ahead and pause the video and see if you can graph the following 2 functions using transformations. Okay, let's check our answers here. So you can see here I drew our parent function. So since the base is between 0 and 1, we actually have an exponential decay. So here's the coordinates of my parent function here and here. And then you can see for f of x, the way we transformed it is by multiplying our y values by negative 1 and then subtracting 3. Our x values were unchanged, and these were our resulting coordinates, giving us a graph that looks like this. So notice it was shifted down 3, which shifted our horizontal asymptote down 3, and then we also had a vertical reflection. For g of x, our only transformation was that our graph was shifted to the left 2. So you can see that I adjusted the coordinates here. Our y values stayed the same. So from our parent function, everything was just shifted left 2. Our horizontal asymptote stayed in the same place. So a common application of exponential functions is going to be a compound interest formula. So here's what the compound interest formula looks like. It's a equals p times 1 plus r over n to the power of nt. So p is what we call the principal amount, which is also known as the starting amount. So how much did you invest in some type of account? R is our annual interest rate, so we're going to write that as a decimal. So if your interest rate is 3, we would say R equals 0.03. N is the number of times your interest is compounded each year. So some accounts, they pay you interest once a year, sometimes they pay you twice a year, sometimes they pay you 12 times a year every month. So we would adjust that for how many times your interest is calculated and paid off. And then T is the number of years that's gone by. And then you can use this formula to calculate how much money you now have after that amount of time. So later on in this chapter, we will be using this formula, but it is a useful one to know, and it's just probably one of the most common applications of exponential functions that you'll see. One thing I want to point out, and this ties into what we were talking about earlier, if you want to compound your interest continuously, we will use base E. We'll actually use a slightly different formula because remember when we have base E, it represents continuous growth. So here we can calculate how much money we have by doing our principal times base E to the power of RT. R is still the interest rate as a decimal, T is still the number of years. But again, we will come back to these later on in the chapter. All right, so now we're going to talk about logarithmic functions, which will tie into exponential functions. So a logarithmic function with base a is defined by y equals log base a of x such that a to the power of y equals x. So first, I do want to point out that by definition, for logarithms, a must be a positive number. A will always be positive, and a will never equal 1. So there is no log base 1. So if you notice the relationship between this statement and this statement, a is the base of my logarithm and the base of my exponential expression. And you can see here that y becomes the exponent. So I like to say that logarithms define exponents. Notice this logarithm is equal to y, which is our exponent. So we can use logarithms to help us solve for exponents. So that's one useful purpose of logarithms. A few special types of logarithms I want you to be aware of. If you see just log of x, we call this a common log. What it means, it's implied that the base is 10. We never write log base 10 of x, but it's important to know that when you see a common log, the base is 10. And this, we read this natural log of x. We will never read it ln x, we'll read it natural log of x, and it's called a natural log, and it's implied that this is a logarithm with base e. So we will write it like this, but it means that it has a base e. So another really important thing to note about logarithms is that logarithmic and exponential functions are inverses of one another. So that's going to come into play when we talk about some properties of logarithmic expressions. So knowing what we know about how a logarithm is defined, let's see if we can evaluate the following expressions. So remember, logarithms define exponents. So here I have log of 1,000. So I want to remind you that this means it's implied that we have log base 10 of 1,000. So when I look at something like this, I'm asking myself, 10 to what power is equal to 1,000? That's what a logarithm means. 10 to what power equals 1,000? Remember, logarithms define the exponents. And we know, oh, that's easy. We know that x would equal 3. Because 10 cubed is 1,000. So this logarithmic expression is equal to 3. Let's try this one. When I read this one, in my mind, I'm saying 16 to what power is equal to 4. That's how we evaluate this logarithm. So I know that if I'm raising something to a power and I'm getting a smaller answer, that means that this should be some sort of fraction, and I know that the square root of 16 is 4, so that means x is 1/2. Remember, if you have an exponent that is 1/2, it means square root. Okay, for this last one, if you ever see something like this, log base 4 of 0.25, it might be useful to rewrite your decimal as a fraction. We know that 0.25 is 1/4. So now it might be a little bit easier for us to evaluate. We're saying 4 to what power is equal to 1/4. So we know that negative exponents cause a reciprocal, so this x must equal -1. So whenever you're trying to evaluate a logarithm, please remember that logarithms define exponents. The base to what power equals this number. All right, go ahead and pause the video and see if you can evaluate these 3 logarithms. Okay, so for the first one, remember I recommend rewriting the decimal as a fraction, and then you can say, oh, 10 to the power of -1 equals 1/10. For part B, 3 to what power equals 27? Oh, 3 cubed is 27. For the last one, 64 to what power equals 8? Oh, 64 to the power of 1/2, aka square root of 64 equals 8. All right, so now we're going to outline a couple important properties of logarithms. So the first one is log of any base of 1 will always equal 0. So the reason for that is any base to the power of 0 will equal 1. So anytime you see the log of any base of 1, it's going to equal 0. And again, if you understand what the definition of a logarithm is, this should make sense. The next one, log base a of a. So anytime your base matches this number, this logarithm is equal to 1. The reason for that is, well, a to the first power is itself, or any number to the power of 1 is itself. Next, if you have log base a of a to the x, it's going to equal x. The reason for this is that inverse property. So remember how I told you that exponential and logarithmic functions are inverses. Here you can see that we have an inverse function plugged into a logarithmic function. And remember, if you plug a function into its inverse, it will always simplify to x. Same idea here. I have a to the power of log base a of x. So here I have a base a exponential function with a base a logarithmic function. I'm plugging an inverse into itself, so my result should just be x. All right, so let's see if we can apply these properties of logarithms to simplify these expressions. First, log base 5 of 1. Remember, any logarithm of 1 will always equal 0. We know this is true, again, because 5 to the power of 0 equals 1, or any base to the power of 0 equals 1. All right, let's look at part B. So here we have natural log of e to the 7th. So just to help us see what's going on here, let's say I rewrite natural log as log base e, and then we have of e to the 7th. So you'll see here that we have a logarithmic function with base e, an exponential function with base e. So we're plugging an inverse into itself, which means we will simplify to simply 7. And again, this is because logarithmic and exponential functions are inverses of one another. Here, for part C, log base 5 of 5, remember anytime the base and this number are the same, the logarithm is equal to 1, because 5 to the power of 1 equals 5, or anything to the power of 1 equals itself. All right, and for part D, this last one, I see 10 to the power of log of 12. So remember that common log, so maybe I'm going to rewrite it like this, 10 to the power of, a common log has a base 10. So you can see here I have a log base 10 plugged into an exponential function with a base of 10. So an inverse plugged into its inverse. And so these will all cancel out, and it should simplify to simply 12. Okay, so the last thing we're going to do is we're going to graph exponential functions using transformations. So let's consider the parent function here, log base 2 of x. I'm going to start by maybe making a t-chart of a couple values that we can start with. So anytime I have a base of 2 or any base, the first x value I'll pick is its reciprocal, so I'll pick 1/2. Giving me a y value of -1, because 2 to the power of -1 equals 1/2. And then I will always pick 1, and I know that 2 to the power of 0 equals 1. So any parent function for logarithms will go through the point 1, 0. And then the last one I'll pick is itself, 2. And I know that 2 to the power of 1 is 2. So these are 3 points I can start with. And I can graph these just to see what our parent function looks like. So we get something that looks like this. So a few things that I want to point out. Here we have a vertical asymptote at x equals 0. And then if you remember that, again, logarithmic and exponential functions are inverses of each other, I do want to point out that if you graphed the inverse of this function, which would be a base 2 exponential function, you get something that looks like this. So it is reflected over that line y equals x. Another thing you might notice is that if you took the coordinates from the function, I'll say big P of x equals 2 to the power of x, which is the inverse of what we're graphing, and you do -1, 0, 1, Well, 2 to the power of negative 1 is 1/2, 2 to the power of 0 is 1, and 2 to the power of 1 is 2. So you'll notice that the coordinates of this are flipped from the coordinates of this, which is what happens with inverse functions. You literally can swap the x and y values. So if you have a hard time filling in a t-chart for a logarithmic function, why don't you make a t-chart for its inverse, and then you simply flip the x and y values. So now that we have some x and y values for our parent function, now we can transform them and graph our new functions. So for this first one, I see that we have 2 transformations. We have a vertical reflection, and we're going to shift to the left 3. So the way this will affect our coordinates is we should subtract 3 from all of our x values, and we should multiply all of our y values by negative 1. So this will give us negative 5 halves, and then we'll have negative 2, and then negative 1, and then this becomes positive 1, 0, and negative 1. Let's sketch a graph to see what it looks like. Alright, so you should get something that looks like this. So remember, our parent function was this one down here. So you can see that if we do a vertical reflection and then we shift everything to the left 3, we should get something that looks like this. Notice that since we have a horizontal shift, our asymptote shifted to x equals negative 3. All right, and let's try this last example together. So here I have 2 transformations. I have a horizontal reflection, so that's going to reflect over the y-axis, and then I'm going to shift up 4. So the way that affects my coordinates is I'm going to multiply all of my x values by negative 1, and then I'm going to add 4 to all of my y values. Here's my original values. So this gives us negative 1/2, 3, and then we have negative 1, 4, and negative 2, 5. And let's sketch a graph and see what we get. Alright, so here we have something that looks like this. So notice this was reflected over the y-axis, so it was reflected horizontally, and then everything was shifted up 4. So first we reflect, then we shift. Our vertical asymptote stays at x equals 0 because we didn't have any type of horizontal shift. Alright, go ahead and pause the video and see if you can give these 2 a try. Again, please start by finding some coordinates from your parent function and maybe sketch a graph of that, and then try to sketch f of x and g of x using transformations. Okay, so here is a sketch of our parent function, and these are the coordinates from the parent function that I use. So 1, 0, 5, 1, and 1/5, negative 1. So for the first one, notice that I'm going to shift my coordinates to the right 2 and then up 2, giving me these coordinates. So from my parent function, here's f of x. So notice that my asymptote shifted to the right 2, and then all of the coordinates went right 2 and up 5. Or sorry, right 2, up 2. And then for the second one, here we have a vertical reflection and a shift down 3. So you can see that here's how I changed my coordinates. I multiplied my y values by negative 1 and then subtracted 3. So I went from this to a vertical reflection, and then I shifted down. So you get something like this. All right, that is all for today's video. Thank you so much for watching.